In this problem, an airline knows that 5% of the people making reservations on a flight from San Diego to Oakland will not show up. Consequently, their policy is to sell 52 tickets for a flight that can hold only 50 passengers. What's the probability that there will be a seat available for every passenger that shows up? This is pretty common practice by airliners. They know that not everyone's going to show up, so even if you have 50 seats, they'll sell extra seats, even though they don't have. Because the probability that everybody shows up is not basically they believe that it's not going to be high, right? So they're just if they sell 52 seats, but only 45 people show up, and everyone still has a seat, everybody's happy, right? Those who missed their flights, it's fine because they missed it, right? Okay, so we want to know the probability then that whoever shows up for a flight, they actually have a seat. Okay, that's what we want to find out. Okay, so if you have 52 passengers have made a reservation, okay, anytime the number of passengers, as long as there's up to 50 people showing up, everybody has a seat, right? The only case when someone does not have a seat is if the 51st and the 52nd customer shows up, okay? So for any given customer, the probability that somebody shows up, so probability passenger shows up is 95%, right? Okay. Then the probability that someone doesn't show up is 5%. So we could think of this as a Bernoulli trial, right? Success means that they show up. Failure means that they don't show up. Okay. And there's 52, so we could think of these as 52 trials, right? So then we're talking about a binomial random variable, right? Out of 52 trials, what are the combination of 50 successes or lower, right? Okay. So if you think of 50 seats or 52 reservations, so 52 reservations. Reservations are reserved passengers. Okay, you could have this person show up, this person show up, this person show up, and then the last three don't show up, right? Or it could be a combination of the first person showing up and then the last person showing up, right? Okay, so as long as there's fewer than or equal to 50 passengers showing up, we're okay, right? So we're really solving for if x is the number of passengers showing up, that's a random variable. Okay, we want to know the probability that x is less than or equal to 50, right? As long as there's fewer than 50 passengers, everybody has a seat and everybody's happy, right? So if I rewrite this, this is the same thing as saying probability of x equals to, let's say we could have 0 people show up, right? We could also have 1 person show up. We could also have 2 people show up, right? All the way to 50 people show up, right? Okay, as long as there are fewer than 50 people, everybody's happy. Okay, right? Now this is very cumbersome, right? You don't want to, do the whole thing, right? This is going to be a very long process. So instead, what we can solve is 1 minus, okay, I'm sorry. So yeah, so what we really want to know then is 1 minus the probability of x equals 51, bracket right there, plus probability of x equals 52, okay? Because in the first try here, we're only missing 2 more outcomes, right? When x equals to 51 or 52, there's no other, you can't have a negative people show up, right? It's either 0 people show up, 1 person, 2 passengers, all the way up to 52, right? So we're only missing 2 cases here, right? 51 and 52. So rather than doing everything from 0 to 50, we're going to do 1 minus the 2 cases that we're missing, 51 and 52. Okay, then we solve this probability, right? So I'll solve the probability of x equals to 51 first. Now, like I said, this is a binomial random variable, right? Because we think of 52 trials, number of success means a passenger showing up. So number of successes in a given number of trials. So if we rewrite this, this is going to be 52 factorial over 51 factorial, 1 factorial. Probability of success here is the probability of someone showing up, so 0.95, so 51st power, and then probability of failure, 0.05, so power of 1. Okay, and then for So the probability of x equals 52 is simply 52 factorial, okay, divided by 52 factorial, and then 0 factorial, right? So this whole thing is just basically 1, right? And then 0.95 is the 52nd power, and then 0.05 to the 0th power. So this is also just 1, okay? It's 0.95 to the 52nd power, okay? So put all this together then, okay? Probability of x less than or equal to 50 is going to be 1 minus, probably, I'll rewrite this, x equals to 51 minus probably x equals to 2. Okay, so this will be 1 minus, if you look at this, I'll just reduce it a little bit. So 52 factorial, this will be 52 times 51 factorial over 51 factorial. 1 factor is basically going to be 1, right? Okay, and 0.95 to the 51st power times 0.05 power 1. So these things cancel, okay? Minus, and this will be 0.95 to the 52nd power. Rewrite this again. This will be 1 minus 52, 0.95 to the 51st power, 0.05 minus 0.95 52nd power. Okay. If you evaluate this, you're going to get roughly 0.741. Okay. So this is a probability that every passenger has a seat, right? So if you sell 52 seats for this plane with 50 seats, there's a 74% probability that every passenger that shows up will have a seat and will be happy. Okay. Let's take a look at this problem. Consider a continuous random variable x with the density function called the exponential density as given in the equation there. Part A, find and sketch the CDF for x, the random variable x. This is the probability density function. Now I want to find the cumulative density function, right? Okay, CDF. What do? I just have to integrate, and I have to find a function for x. Okay, so big F of x, I'm going to write as the integral, since this is defined from 0 and on, to be 0. And I'm going to set this to x because I actually want a function out of this, right? Okay, so it'll be e to the negative, I'll put a dummy variable here, t dt, okay? And when I integrate this, this will be minus e to the negative t, and going from 0 to x, okay? So then if I evaluate this, this will be minus e to the negative x minus a minus e to the negative 0, right? So this whole thing is just 1, right? So what you end up getting is 1 minus e to the negative x, okay? So this function is now very easy to solve, right? Okay, if I sketch this equation, this function, okay, this is my big f of x, x right here, okay? So we're gonna, when x equals to 0, this whole thing is 0, right? Just plug in 0 to this x value here. Okay, it says e to the 0 power is 1. Start at 0, okay? As x gets bigger and bigger, if you think about it, this is 1 minus 1 over e to the x, right? As x gets bigger and bigger, okay, it's going to asymptotically reach 1 because that fraction 1 over e to the x becomes smaller and smaller, right? So at 1, okay, we're going to asymptotically reach 1 like this, right? So that's the sketch of f of x. Okay. Part B, I want the mean and the variance of x. So if I want the mean, I just need the expected value of x, okay? To get the expected value of x, again, it's very simple. It's the integral of x times f of x dx, right? Okay, so then this would be integral. In my case, this would be 0 to infinity, okay? X times e to the negative x dx, okay? And this is where we need integration first. U equals to x, du equals to dx. dv is e to the negative x dx. V then must be negative e to the negative x, right? So if looking back at your earlier math courses, integration parts comes into play here. So it's going to be uv minus v du, right? So, okay, uv, so negative x e to the negative x, and this is going to go from 0 to infinity, minus v du, so 0 to infinity, v, which is e to the negative x, with the minus, I'm going to take the minus out, okay? And then du, which is dx, right? Okay. If you look at this first portion, okay, as x approaches infinity, what happens to the entire term? It's going to go to 0. And as x goes to 0, this also goes to 0, right? So this whole thing is just equal to 0. If you're unclear on this, look back at our lectures, and you'll see I go in detail why this is 0, okay? So we're just left with this term here, okay? So integrate again, this will be minus e to the negative x when I integrate from 0 to infinity, okay? So this will be then minus e to the negative x as x approaches infinity, minus minus e to the negative x as x approaches 0, okay? So then this whole thing, as x approaches 0, this, what happens to this entire term as x approaches 0? This whole thing becomes 0, right? Okay. Now this will be plus, because I took the minus sign out. As x approaches 0, okay, this becomes e to the x where x equals 0. This just becomes 1, right? Okay. So then this whole thing becomes 1, right? So the expected value of x equals to 1. Okay. Let me finish out. Let me do the variance up here. I want the variance of x. Okay. That's simply the expected value of x squared inside the brackets, right? Minus entire quantity expected x squared, right? So this portion we already know, we found down here. So we know this whole thing is just 1 squared, right? So we only have to evaluate this portion here, the expected value of x squared, okay? So how do I get this how do I evaluate this expression? Very similar to what I had earlier, but it's just x squared, right? So it's integral of 0 to infinity of x squared, okay, f of x dx, okay. Again, further go in there, this will be right over here, 0 to infinity, x squared, and my f of x is e to the negative x dx. Okay, let me erase this one to avoid any confusion, okay. Okay, so I have this expression. I'm going to use uv substitution again, right? So it's going to be it's going to be x squared du is 2x dx, and then let's see, v and dv. dv is going to be e to the negative x dx. Then v is minus e to the negative x. I think that's it, right? So then I'm going to use uv substitution again. uv is going to be x squared. V is minus, so make some room here. Take a little bit of space over here. This whole thing will be minus x e to the negative x. That's the uv portion. I'm sorry, this is x squared. Okay, where x goes from 0 to infinity, minus v du. So integral from 0 to infinity. Du is 2x. Okay, and then you have v, which is minus e to the negative x dx. I'm going to take the minus out. Okay, then this becomes positive. Okay, I'm going to rewrite this, get rid of the parentheses, and I'm left with e to the negative x dx. Okay, so this whole portion goes to 0 as well. Same logic as I discussed in the lecture. You can evaluate again, and you need to convince yourself why it's 0. So we're again left with this expression over here. Now, you might want to, you could do UV substitution again here, but I don't want to repeat what I already did. If I take a look at this carefully, if I rewrite this, I can rewrite this as 4 times the integral of 0 to infinity of 1/2 x e to the negative x dx, right? Okay. Sorry, not 2 times, right? Yeah. let me, not 4 times, 2 times, right? I can rewrite this as 2 times x, push this over here, so you can see. This would be x e to the negative x dx, okay? Look at this carefully. This is what we evaluated earlier, right? That equals, this whole thing equals the expected value of x that I evaluated earlier, okay, down here. Okay, that's what I evaluated, right? So then this whole thing just becomes 2 times 1. Okay, getting a little crowded here, so let me just change the color, and then hopefully you can follow along here. So I'm going to summarize everything here. Okay, the variance of x then is the expected value again for x squared minus the expected value of x, the whole quantity squared. Okay, this first portion I just calculated, it's 2, right? I calculate over here, it's 2, right? It's 2 minus 1 squared, okay? So this whole thing is just 1, right? So my variance for this problem is 1. My expected value is 1, and the variance is also 1, okay? So hopefully this will explain, it shows you again the integration by parts, and also how I reuse what I already calculated for the expected value back when I'm doing the variance. We're ready now to do part C. I want the probability that x is between 1 and 2. Oops. So I want this probability. So this is just a straight application of the integral. So my limits of integration is 1 to 2, and my function is f of x dx, right? So it's be 1 to e to the negative x dx, right here. So this would be minus e to the negative x, 1 to 2, okay? So it'd be minus e to the negative 2 minus the minus e to the negative 1. If I rewrite this, it would be e to the negative 1 minus e to the negative 2, which is approximately 0.2. So this actually shows this is the area under a curve, okay, between 2 and 1. Okay, so if you look at the exponential function, this is my PDF. Okay, this is the area between x equals to 2 and 3. I'm sorry, 1 and 2. The area between 1 and 2. This area is roughly 0.8 here, roughly 233. In this problem, we have a fugitive trapped in San Diego sewer system. This problem is inspired by the movie Fugitive with Harrison Ford. There's a scene in the movie where he's moving through the sewers. And if you haven't seen that movie, it's a classic, The Fugitive. And I think U.S. Marshals is the sequel to it with Wesley Snipes. This is probably a very old movie for you guys, but so there's a fugitive in the sewer system. There are 3 tunnels. Okay, so there's 3 tunnels, and the fugitive is standing right in front of those 3 tunnels. The first tunnel, the second tunnel, and the third tunnel. If the fugitive takes the first tunnel, then after 2 hours, the person reaches safety. Okay. If the fugitive takes the second tunnel, they're gonna wander around, okay, but eventually come back to the same spot after 3 hours. Okay. If the fugitive takes the third tunnel, then they'll again wander around, okay, and eventually come back to the same spot after 5 hours. Okay. The key here is that the fugitive, when he comes back, he's disoriented, right? So he could again take the same tunnel even though he took it before, right? And at all times, equal likely to choose any of the tunnels, right? Then I want to know the expected length of time until the fugitive reaches safety. Okay. So in this problem, we got to determine, well, we got to set the events, right? So I'm going to set x equal to the event. X is actually the time until fugitive reaches safety. Okay. And then y equals to the tunnel the fugitive chooses. Okay. So at any given point, the fugitive can choose tunnel 1 or tunnel 2 or tunnel 3, right? Okay. That is equal probability. Okay. We want to know the expected time until the fugitive reaches safety. So we actually want to know the expected value of x. Okay. We want to know the expected value of x, not knowing which tunnel he's going to choose. right? So if I write this out, so I think the key to this problem is understanding. Okay, let's draw it this way. Okay, this is an original scenario. Okay, and I have this person. If the fugitive picks door 2, he's going to travel 3 hours, but eventually he's back to the same spot, right? Okay, he's facing. It's as if he's facing 3 sets of new doors, right, or tunnels, right? The expected time to safety in the original situation is expected value of x. Okay, right. When the person comes back to the original spot, the expected time to safety is again the expected value of x. Okay. Only difference is it took them an extra 3 hours to get to this original spot. Okay. So if I write this whole thing out, the expected value of x is going to be the expected value until safety, given that the fugitive chooses tunnel 1, the probability the fugitive actually chooses tunnel 1, plus the expected value of x, given the fugitive chooses the second tunnel, probability that he actually chooses tunnel 1, probably the expected value of x, given he chooses tunnel 3, and the probability that he actually chooses tunnel 3. Okay, all of these probabilities, they're the same, right? It's always 1/3. It's always 1/3, equal probability, right? Then we need to figure out each one of these expected value of x given y terms, right? So let's start with the expected value of x given y equals 1. Okay, this is saying, let me use a highlighter here. Or laser. If the person starts here and it chooses door 1, how long does it take for him to reach safety? Just 2 hours, right? Okay, so the expected value of x given y equals 1 is just 2 hours, right? This is simply 2. Okay, the expected value of x given y equals 2 is a little different, right? Because let's get the laser pointer back. This person starts here, okay, takes tunnel 2. He's going to spend 3 hours, but then come back to the original spot, right? Okay, so the expected time of safety for this person then is 3 hours plus. Now you're at the original spot. It's expected value of x again. So it's as if I use the diagram on the lower left hand side, if you choose tunnel 2, it takes 3 hours plus expected value of x. You're back to the original spot. This is expected time until you reach the safety again, right? So I just have to add those two pieces together to get the right expression. Okay, so expected value of x given y equals 2, simply 3 hours, because you spent 3 hours wandering around, plus the expected value of x again. Okay, and the same logic now for expected value of x given y equals 3. 5 additional hours, but now you're back to the original spot, expected value of x. Okay, so I am now ready to solve and get an answer. Let me write it over here. Okay, so then expected value of x is going to be 2 times 1/3 plus 3 plus the expected value of x times 1/3 plus 5 plus expected value of x times 1/3. Okay, this whole thing equals expected value of x, right? So I'm going to multiply 3 to both sides. I get 3 expected value of x equals 2 plus 3 plus expected value of x plus 5 plus expected value of x. Okay, so I'm going to move things around. I'm going to move it to the left side. I'm left with expected value of x equals to 10. Okay, so this is my answer. This is the expected time until the fugitive reaches safety. In this problem, we have a random variable x, and it's given that it's a uniform random variable. So the box from 0 to 1 of height of 1. So the density function is f of x equals 1 for x greater than equal to 0, less than equal to 1. What is the beta? Okay, so this problem is very simple, right? Look at A. Okay, you have a PDF. Okay, it says it's a box from 0 to 1. So 1, 1. This is my box. Okay, the area under the curve here has to be 1, right? Okay, base 1 times height 1. So area is 1. Okay, so this is a PDF of my uniform distribution. Okay, what's this median? Median means 50% is to the left, 50% to the right. So exactly half of this, right? So then x has to equal 0.5 at the median, right? Okay, so what's the median? 0.5, right? That's my median. That's the 50% mark, right? Oops, sorry. Okay, that's the 50% mark, right? Okay. Part B, okay. Consider the following random variable and probably mass function is given. What's the variance of x? Again, I'm going to use that definition. Variance of x is going to be the expected value of x squared minus the expected value of x minus squared. Okay, let's start with the easy one. Expected value of x. I'll go right over here. What's the expected value of x? This is a discrete random variable. It's just a sum of xj probability of xj. Okay. If I write this out, this will be 2 times probability that x equals 2, right? Okay, plus 3 times the probability that x equals 3, plus 4 times the probability that x equals 4, plus 5 times the probability that x equals 5, right? Okay, when I put all that together, it will be 2 times 0.1 plus 3 times 0.2 plus 4 times 0.3 plus 5 times 0.4. Okay, I think if you evaluate this, you should get 4. Okay, so, so this is the expected value of x. Okay, so I know this part will be then 4 squared. So expected value of x squared then, how do I get this part? This is simply the summation of j, the index sign for j, xj squared, and the probability of xj, right? So this is a very simple problem, right? So it's 2 squared, probably x equals 2, plus 3 squared, probably that x equals 3, plus 4 squared, probably that x equals 4, plus 5 squared, probably that x equals to 5. 4 times 0.1 plus 9 times, this is going to be 0.2 plus 16 times 0.3 plus 25 times 0.4. Okay, this ends up being 17. So therefore, variance of x then has to be 17 minus 4 squared, which is 1, right? Because 4 squared is 16. In this problem, we have a website for a home pregnancy test, and it cites the following. When the subjects using the test were women who collected and tested their own samples, the overall sensitivity was 75%, the specificity was 52%. Suppose a subject has a positive test and that 40% of women taking pregnancy tests are actually pregnant. What is the probability that the pregnancy given, what is the probability of pregnancy given a positive test? Okay, so again, there's 2 events here, right? I'm going to set up those events. A means the subject is pregnant. Okay, pregnant. Okay, so A complement means the subject's not pregnant. Okay. B means B is an event where the pregnancy test is positive. And B complement means that the pregnancy test is negative. Okay. What's the probability that the pregnancy, what's the probability of pregnancy given a positive test? So what I'm trying to calculate is the probability of A given B. Okay. That's what I want to calculate. So if I use the conditional probability definition, this will be the probability of A and B. Okay, and this is give over probability of B. Okay, I can rewrite the numerator again. This is the probability of B given A, probability of A, and then my denominator I can rewrite as probability of B given A, probability of A plus the probability of B given A complement, probability of A complement. Okay, so I think really the only hard part here is figuring out just in these individual terms. Okay, probability of A here, it tells you in the problem that 30% of subjects who take a test are pregnant. So probability of A is 30%. Okay, which means the probability of A complement has to be 70%. Okay, it gives you the sensitivity and specificity, and that's going to help us, right? So probability of B given A, what does that mean? That means the probability that the pregnancy test is positive, given that the person is pregnant, right? Okay. So let's look at the sensitivity, definition of sensitivity. Probability that the test is positive, given that the subject is pregnant. So this is exactly what the sensitivity tells us, right? So this value is 75%. Okay. So then, so that's going to give us our sensitivity. Now, if we want the probability of B given A complement, okay, that's saying what's probably positive given the person is not pregnant, right? Okay. Let's look at the definition of the specificity, right? Okay. The probability that a test is negative given the subject is not pregnant. So this is what this is actually telling us. This is a probability of B complement, right? Not pregnant, given that, the probability that the test is negative, given that the person is not pregnant, right? That value is 52, which means probability of B given A complement is simply 0.48, because if you add these two up, they have to add up to 1, right? So given A complement, B plus BC has to add up to 1, right? So let me write this over here. It's 0.52, okay? So we know this value then is 0.48. Okay, so if I then plug the values in, it's 0.75, 0.3, 0.75, 0.3, plus 0.48 times 0.7. Okay, if I evaluate this, this will be roughly 0.4.